Happy Monday, everyone. I'm at Oakmont having a lot of fun with Common Core today. You're going to be extremely well behaved for this sub. I know she's doing me a favor by helping out today, so please be cooperative. After I'm done with the lesson, get to work on your assignment. And please, don't be disruptive. Do what you're supposed to do. Max? Alright, so this section deals with functions. I want to remind you, if you don't have your parent graphs wired, you can go to the Granite Bay website. The first page, I put up that link for you. On the first page, if you scroll down below where it says important review notes, if you open that, you'll see there's the factoring review is still there, but the parent graphs are there also. So if you click on that, you open it, you'll see a pretty good review with parent graphs talking about stretch factors. We're going to have horizontal stretching going on, absolutes, quadratics, cubics, cube roots, square roots. Everything's there. So you're going to want to take a look at that. And obviously that page just disappeared, so we're just going to have to not worry about that. So in this section 4.1, we're going to start talking about functions again. You've done this to death over the years. Remember, a function is a rule that assigns every element in the domain, the x's, to one and only one element in the ranges, the y's. Or for every x, there's one and only one y. We are going to be using function notation almost exclusively, so really pay attention to that. G of u is equal to v means u is the domain element or the input, and v is the range element or the output value. As an ordered pair, it would look like this, u comma v. So when you're writing them in ordered pairs, this is what I want to see. All right? Remember, a function, each member of the domain is paired with one and only one member of the range. This is a linear function in function notation. We're not interested in switching the f of x to y anymore. We want to work with it in function notation. The x's are the domains. You're going to be giving domains in interval notation usually. We have to use the set notation here. So you notice, see the set with this symbol right here, the little braces is what they're called. And then x for your domain, it's x. And then this vertical line here means such that, and then give me whatever the domain is in interval notation. And then similarly with the range, you're going to do the same kind of deal. The range, all values of y, such that, and then interval notation. Remember, this stuff has to have the braces around it. And it could be in function notation as well. It could be f of x, such that, and then the interval notation. And I'll give you some examples of that so you can see it here. The graph that we're looking at here is in blue. The graph that we're looking at here is in green. So here's the graph. I'm just going to highlight it for you. And what I want you to imagine, if you're trying to figure out what the domain is, imagine all of this yellow that I just highlighted, all of it drips down the page where the blue is and lands on the x-axis. What is covered on the x-axis, in this case in yellow, would be from here to here. That is what your domain is. Your domain for this function right here is going to be from 3 to 15. So off to the right here, we have domain is all values of x such that we go from 3 to 15. Notice we're using brackets hugging the 3 and hugging the 15 because these points are solid on the ends, not open. So we're including the x equals 3 and we're including the x equals 15. The notation has to have the braces around the whole domain. Then imagine that we pushed all this yellow, again, imagine we pushed all the highlighted yellow, but this time along the purple lines over to the y-axis, and we got yellow all over the axis. I'm going to highlight this for you on the axis right here. And that's where the yellow would end up on the y-axis between the 7 and the 19. So your range is all values of y such that all the y values between and including 7 and 19. That's our interval notation. Oh, we got an illusion for you. If you've never seen this before, take a second and see if you can figure this out. Photoshop's amazing, isn't it? All right, so here you have a function. I know it's a function. Hopefully you know it's a function. It's quadratic. If we look at this, I want to be able to identify domain and range. Because it's quadratic and it's y equals, hopefully you already know what the domain is. We don't even have to graph it, and hopefully you know the domain is what? Okay, so maybe we need to graph it. So let's take a look and see. If we graph this, you get this parabola. The vertex, you may remember, is going to be at 4, 3. And you can see here's my vertex right here at 4, 3. It's horseshoe up with a vertical stretch factor of 2. So if you're graphing it, you're going to make your parent graph y equals x squared. Your translation vector is 4, 3. Also your vertex. And your vertical stretch factor is 2. So from 4, 3, right 1 up 2, left 1 up 2, right 2 ends up going up 8. 2, 4, 6 would be up here. And left 2 up 8. And we get this parabola. Now, again, think about the yellow paint on the axis. This parabola keeps getting wider and wider and wider, so your domain ends up being all reals. Now, if we push all these points, if we were to paint this and you look at it, it's a purple color. If we push it all on the y-axis, where does the range start? It would start at the lowest value, because this is a minimum, and that would be at 3, and it would go all the way to infinity. We hug the 3 because 3 is included as part of the range. If it was an open circle, we would shun the 3. Now this one's different. You guys haven't seen this. Notice it's not y equals x squared, it's x equals y squared. And if you had to make a guess, what's going to happen on this one? Is it still going to be a parabola? How's the parabola going to open? Well, when it's x equals y squared, and we graph it, you get a sideways parabola. And that's actually the parent graph for the sideways parabola. But what do you notice about this graph? Remember, look at what this section is called. 4.1, functions. What do you notice about this? Not a function. It's not a function because when you look at your x's, 1x, let's say for example, when x is 4, y is 2, but y is also negative 2. That means you have 2 y values for 1x. That's not what the definition tells us. Do we still have a domain? Of course we have a domain. If you squish all these points up to the x-axis, you'd get points right along here. So if those are where the points would land, there's your domain. All values of x such that x is greater than or equal to 0, from 0 to positive infinity. Now what about your range? It's going to keep getting wider in both directions. So your range is going to be all reals, from negative infinity to positive infinity. So this graph right here, x equals y squared, that's a new one for us, but the problem is it's not a function. So we would end up having to restrict that range in order to make it a function. Also a new situation for us. Okay? X squared plus y squared is equal to 9. Now that's a graph of a circle. It's not something that you're going to be overly familiar with. But if you were to take it and solve for y, in other words, we subtract the x squared, so we have 9 minus x squared, and then square root both sides, we get the plus minus 9 minus x squared under the radical. When you have that, the 9 minus x squared has to be greater than or equal to 0. So if you solve that, you're going to get 9 has to be greater than or equal to x squared. Or 3 has to be greater than or equal to the absolute value of x. If the absolute value of x is less than 3, you're going to be between 3 and negative 3 on your graph for your domain. So when you look at this domain, between negative 3 and positive 3, that's where your domain values are. When you plug those values in, you're going to get your range values. Take a look at what the graph looks like. The graph is a circle. Your domain goes between 3 and negative 3, but look at the range. That's also between 3 and negative 3. So when we look and identify our range, we get the same thing in this one. And that's a coincidence, and it's because the circle is centered at the origin. But nonetheless, when you see the x squared plus the y squared, with the same coefficients in front of the x and y, you're going to get a circle. We'll talk more about that later. It's not that critical for us in this section. Just another one for you to look at. What else do you notice about the fact that you generated a circle in terms of this section? Not a function. Now, what are we going to do when we have something like this? I just want to know what the domain is. So if you look at the a function, g of x equals 1 over x minus 7, what is preventing a domain value from being used? It's going to be where the denominator becomes 0. So what value of x makes the denominator 0? Good, 7, very good. How do we describe the domain? We'll take everything but the 7. And there should be braces around this. So we should have the braces notation here. If you look at the b situation here, now we're looking at a half of a circle. The reason why it's a half circle is because it's not plus or minus the square root of 1 minus r squared. Again, the radicand, the 1 minus r squared, has to be greater than or equal to 0. So if you solve that, 1 has to be greater than or equal to r squared, and the absolute value of r has to be less than or equal to 1. That puts your domain at between negative 1 and positive 1. So we're setting the radicand to be something greater than or equal to 0 and then solving for that x value. Count the legs. You know this is a mutant. These art people are good, huh? All right, so now we're looking at graphs. Now this graph is just a piecewise function that was graphed for you, and you're just looking at it. Open circle at the right-hand side on the top. The left-hand side at the bottom, this is not an open circle, it's meant to be a closed circle. Not trying to be misleading at all. So your domain are your x values. What is the smallest x can be? What's the biggest x can be? Again, if you were to go along the x-axis, where are their points? It's going to be right along here. What values of x do you get from 1 to 6? Do the same thing with the y's. take a look. Where are we going from the y's? The highest we can go is here, and we go down to here. So what are we looking at? For your range values, you're talking about from -3 to 7. Notice that we're including the -3 hug on the left, but we shun the 7. And in the domain, we include the 1, but not the 6. And again, in both cases, you need to have the braces around these. If you're like me, you're going to need to practice making those. This is not what I'm looking for. And I know that some of you are going to give up on this quickly, but you need to practice it. Okay, so this notation for this squiggle that I have up here is meant to be not getting any taller on the right-hand side. It's going to stay pretty horizontal. But on the left-hand side, we really are implying that this is going to keep going down. So when we look at the range, we have a maximum value of 3, and we have a minimum value that it just goes to an infinity situation. So we're going to -infinity all the way up to and including the 3. Don't forget the braces. On the domain, it's going left and right onto infinity, so your domain is, we really want everything there. So, again, don't forget your braces. We go -infinity to +infinity. That's all reals for your domain. If you look at this squiggle, notice we have an open circle on the left, and it goes to infinity on the right. And we do go up and down and repeat a little bit, but your domain starts at 1 and goes to infinity. Your domain starts at 1, goes to infinity. Notice we're shunning the 1 because it's an open circle. Your range, a little bit different. We don't start the range at the open circle because that's not the highest value for y. The highest value for y occurs here when y is 4, and then goes down to -infinity. So we want to be from -infinity all the way up to and including the 4. Now as far as this goes, we're really not going to use that kind of a notation right now to identify the roots. Because if we talk about domain range and then we talk about the zeros, here's the 0 for this function. 1, 2, 3, 4, 5.5. So your root, you might say, is at -5.5, 0. If you want to say that it's -5 3/4, that's fine. We don't have a way to identify specifically what the root is right now. This is just a scribble on the page. So you're looking at it, doing the best you can. For this one, you're going to say the roots, and then just ballpark it for me. It's 1.20. It is 4.30. That's not what that says. Try it again. 4.30. And then the last one, 1, 2, 3, 4, 5, 6, 7, 8. That would be 8.50. Okay? Don't make that overly complicated. We got nothing at the bottom. Okay? So here we again have this situation where we have a rational function, but we have a quadratic in the denominator. So if there's a quadratic in the denominator and it's +1, what are the values of x to make the denominator 0? You're right, there aren't any. So that means your domain can be anything from -infinity to +infinity. Now your range, there's going to be a restriction on the range. There's going to be a horizontal asymptote at y equals 0 because 1 divided by infinity squared is going to be 0. So if you were to look at the graph of this, you could graph it, plug in a few points, and that might help you with the graph. If you put in a 0 for x, 1 for y. If you put in a 1 for x, get a half. -1, you also get a half. That might be enough for you to see the way this graph is going to go. It's going to max out at 1, and it's going to be asymptotic at y equals 0. If you can't remember how to find the horizontal asymptote, in your calculator you can plug in a 10,000 for x. So you get 1 over 10,000 squared plus 1, round that decimal to the nearest tenth, and that will give you your horizontal asymptote every time. Your domain, all reals. Your range goes all the way up to 1, but it can't get to 0. So your range will be from 0 to 1. We shun the 0, and we hug the 1. Don't forget, put braces around your answers. It's going to take some practice to get back into the functions that you haven't worked with in a long time. Now, in this example, they're saying, hey, is this a function? And the answer to that is going to be no. Your graph is an absolute value. Automatically, you know absolute values have a shape of a V. Well, this V is going to be starting at the origin, but it's going this way. And this way, so left and only to the right with a top and a bottom instead of a V that goes up and down. It's a left-right V. So if you look at this, first off, tell if the graph's a function. No. If so, give domain and range in zeros. Well, you could still give domain and range in zeros, but it's not a function. The domain is greater than or equal to 0. From 0 to positive infinity, hug the 0. The range is all reals. The only root that you have, or 0, is 0, 0. But this is not a function. This is a parent graph, y equals the square root of x. We would want to write it probably y equals the square root of negative x and then minus 3, like this, so that you can see that there's a horizontal stretch factor of -1. B is -1, the reciprocal is -1. The translation vector is 3, 0, and the parent graph is y equals root x. So parent graph, y equals root x. Horizontal stretch factors, the reciprocal of b, so it's going to be -1. And then the translation vector is going to be 3, 0. When you look at the graph of this, you get your half parabola. Because of the horizontal stretch factor of -1, instead of right 1 up 1, right 4 up 2, right 9 up 3, we go to the left 1, left 4, and left 9. So you get this half parabola. Makes it easy to identify, if you have your graph, it makes it easy to identify your domain. Your domain value are the x's, and that's from -infinity to 3, including the 3. And it's easy to see the range when you have the sketch done. You start at 0 and you go up to infinity. Those of you who like to ride bikes, watch this guy. No thinking involved, no planning, and definitely didn't pass his math class. If he had, he would have moved that ramp closer. What are you thinking about? All right, so now we're going to look at the graph. We're back to a parabola, parent graph. Again, you can go through this process, parent graph, vertical stretch factor, all that. When you sketch out the graph, we get a nice pretty parabola. Vertex is going to be at 1/2 -6 1/4. Vertical stretch factor, 1. So you can figure that out. How do we find the vertical stretch factor? It's A. How do we know the parent graph? It's y equals x squared. Vertical stretch factor, 1. Translation vector from standard form, opposite of b over 2a, is going to give you a 1/2. when you plug that in, you're going to get 25/4 negative. So domain, again, all reals. The range is going to be greater than or equal to negative 25/4. And the roots, you can see, are going to be at 3, 0 and negative 2, 0. So you can list all of that. Domain is going to be all values of x such that we're going to go from negative infinity to positive infinity. The range is going to be all values of y such that, now your smallest value is going to be negative 25/4, and it's going to go to positive infinity. Don't forget, we shun the infinities. And then your roots, you can find those by factoring or looking at the graph. 3, 0, negative 2, 0. This is a piecewise function. You did them in Algebra 1, you did them in Algebra 2. So you have to treat each of them as separate pieces. So for example, the top, this function g of u is going to equal 1. The second row says g of u is going to equal 0. And the third one says g of u is going to equal negative 1. Well, if you look at those things, they're all lines. Y equals 1. That would be a horizontal line. It would look like this. Y equals 0. That would be a horizontal line here. And y equals negative 1 would be another horizontal line. Now, like that, you don't have a function. That's why we have to break up the pieces. It says we want to use 1, but only when u is greater than 0. So in order to get u greater than 0, we're going to come here, and then we're going to go with an open circle around here, because we're not including when x is 0. Then it says, well, for the second one, we're going to equal 0, but only when u equals 0. So instead of a whole line, we're going to get just 1 point, 0, 0. And on the third one, g of u equals negative 1, we only want that when u is less than 0. So we only graph this side of the piecewise, and we open circle here. So now it passes the test for a function. Each x goes to 1 and only 1 y. Your domain is all reals. U can be anything. Your range is g of u, and g of u can only be 1, 0, and negative 1. So your domain, it's all values of u such that we're going to go from negative infinity to positive infinity. In your range, is going to be all values of g of u such that we're going to go negative 1 union 0 union 1. And we hug those because those are the only 3 solutions we can have on the y side, the g of u side. You probably remember this vertical line test. It's just the last thing I want to mention before. If you're looking at a picture and you take any vertical line and you move it across your graph, if you only hit 1 point at a time with the line, if the line only touches 1 point at a time like I am here, then you have a function. So this is yes, function. If you move the vertical line, now here we only hit 1 point, but everywhere else we're going to hit multiple points. That fails the vertical line test, so we have not a function. 1 second. This is your assignment. Please be cooperative with the sub. I'll see you tomorrow.